There are two very common ways to create X-rays. On one hand, there is Bremsstrahlung, where fast-moving charged particles like electrons hit a target, for example a piece of tungsten, and they are being decelerated, and a loss of their kinetic energy is emitted in form of photons. This is the principle of standard X-ray tubes. On the other hand, there is X-ray fluorescence, XRF for short, where you use an already existing source of photons, for example gamma or X radiation, to ionize an atom, which can lead to electrons being knocked out of inner shells. Now electrons of higher shells fall into the resulting gap, emitting characteristic X-rays in the process. Characteristic means in this case the photon energy varies between different elements and even between different shells of one and the same element. There are many commercial types of XRF devices for material analysis. Our piece of primary uranium ore here is a relatively safe source of gamma and X radiation. Together with our RadiaCode-102 gamma spectrometer, we will try to analyze this strange coin from a country worshipping old women and maple leaves. Please keep in mind that this is not an ideal setup. The energy resolution of this device was never meant to differentiate between tiny differences in soft X-ray energies. Here we have our setup, lead bricks for unnecessary radiation protection and some additional backscatter, a piece of acrylic to keep the beta radiation from influencing the spectrum, and a small holder for the coins. The first step is to record a spectrum with this very setup, not including the coins. Some time has passed. The spectrum is now saved and labeled. Let's add the coins and start a new spectrum. We are done here. Before we look at the results, we should see what we can expect exactly. I really recommend this page called xrfresearch.com, where we see a perfect spectrum of the low energy X-ray emissions from pure silver and many other elements. If we are really lucky, we will see a 3 keV sum peak to the left, which is far out of spec for our device, which is rated for a range of 20 to 3000 kiloelectron volts. On the right side, we expect a sum peak from roughly 22 to 25 keV. Anyways, let's check out the results. We save our first spectrum as a background, then we load the second spectrum to the viewer and subtract the background. The tiny 3 keV sum peak shows up in the logarithmic depiction, and the sum peak from roughly 22 to 25 keV looks nice even in the linear depiction. The giant quote-unquote peak to the right is just additional backscatter from the coins